I am Dr. Gawali Prashant, working as an associate professor in physics at Bairji Smarak Mahavidyalaya, Basmat, Maharashtra, India, affiliated to Swami Ramanand Tirtha Marathwada University, Nanded. My research topic title is the effect of the size and temperature on dielectric parameters of pigeon and chickpea at microwave frequency. The dielectric material are those materials which increases the storage capacity of the charge. In case of the condensers, they are used in the condensers capacitors. And here I have selected the topic, that is the size agriculture product I have selected. In case of the solids like agriculture seeds, it is not possible to define solid bulk exactly. So we assumed the finest, smallest crushed grain size in powder form, that size, smallest size, as a solid bulk. And these are used for the comparison of the correlation formulas between the powder and bulk. For that, here we have defined one factor which is based on the density. That factor is the relative packing factor. Relative packing factor of the sample or material of the pigeon pea and chickpea is that it is the ratio of the density of different grain sizes powder to the density of the finest or smallest crushed grain size particle. So that factor is also used, that is denoted by delta R. Here in brief, here I have find out the dielectric parameters, dielectric constant, dielectric loss in of pigeon pea and chickpea at the frequency of 9.85 gigahertz. And by using these findings, we can find out the conductivity, relaxation time, the energy parameters, and all these measurements can be carried out at various grain size materials, which is in microns, and temperatures at 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, 50 degrees Celsius. So these values you have determined by using this microwave X-band setup. These values, epsilon dash and epsilon double dash, these values we have verified by using the correlation formulas, that is like Langevin, Schillinger and Bochers. And just it is found that there is a fair agreement between the experimental and theoretical values. And from that, this work confirms that that we have assumed our estimation is of the polarized material as a solid bulk. It confirms. Here the actual the laboratory setup of microwave X-band, where the X-band setup it varies the frequency between 7.1 or 7 to 11.2 gigahertz. Here we have used the 9.85 gigahertz microwave frequency. This is actually the components of the parts of this experimental setup. They are near about 13-14 parts components. Where the 11th, you can see the dielectric cell. The 11th number is the dielectric cell. Dielectric cell is that sample holding cell where the sample or the powdered form of the chickpea and pigeon pea that has to be inserted, or you can put that sample step by step. Then here I have given the chemical composition of pigeon pea chickpea, the procedure of how we have prepared the material in various sizes. Here I have taken the micron size of the material, that is 50 micron, 200 micron, 500 micron, and 2000 micron. These four types of grain size materials we have prepared, and that material is to be separated. That material is to be separated and transferred into glass bottles. And when at the time of observation, just to open at the time of observations. So just avoid the moisture content. Four samples of various sizes, that is 50 micron size, very smallest size of the powdered material, that chickpea and that pigeon pea. Then 200, we have taken the 100 size, 50 micron, 100, 200 and 2000 sizes. And the relative packing factor has determined, and these we have find out the dielectric parameters by the formulas which are given, that is epsilon dash, epsilon double dash, sigma p, tau p, where the these lambda 0, lambda c, lambda z, these are the known values or known wavelengths which are we know these values. Just you have to find out the lambda d by using the experimental setup, that is the guide wavelength. Here I mentioned the relative relations between the relative packing factor delta R and dielectric constant, loss, relaxation time, relative that conductivity. Just these four graphs of pigeon pea sample, and these four they are of the chickpea samples. From that we conclude that that is the effect of the temperature on dielectric values. As the temperature across these samples increases, then it is found your values, temperature increases, then the dielectric values, that is epsilon dash, epsilon double dash, they are in decreases. And this is due to what happens when the temperature increases, the number of collisions of the particle in the sample there increases, and therefore there is loss of energy, more energy is to be lost, and for that the dielectric values they are to be decreases. The second one, what is the effect of the density on these values? As the density of the sample is increases, when the material or sample is more compact, then the dielectric values it is found it is to be increases by increasing the compactness. That is due to when the compactness increases, then there is no micro cracks developed in the sample, and when the materials or molecules they are very close to each other and the compactness increases, and automatically the hindrance it is produces due to the process of polarization, right? And just I have mentioned here one table. These values we have checked by using the formulas Bocher's and triple L formula, and just I have given the example of, just you see the 20 degrees Celsius. For 20 degrees Celsius, the measured value of dielectric constant by using X band, that is 3.41, and just by using Bocher's, and it is nearly equal, and it shows that there is effect of, and these formulas, correlation formulas have the fair agreement. Right, and just I mentioned the feature scope. Definitely in the grading stations, by using these dielectric parameters, if you design the moisture meters, that will be very accurate moisture meter which affects on the quality control. And these are the references I have given. I have published my papers in the Indian Journal of Pulse. If you go detail, just you go through these papers. Okay, I have to stop here. Thank you.